Okay, hello everyone. These are a few questions on chapter 28, magnetism, and I might solve one or two questions on the previous chapter at the end, chapter 27, electric circuits. So first question is about the cyclotron, which is a device we discussed during the lecture. A cyclotron designed to accelerate protons, in this case, has an outer radius of 0.35 meters. The protons are emitted nearly at rest from a source at the center of the and are accelerated through 600 volt each time they cross the gap between the D's. D's means D1, D2, discussed again within the lecture. The D's are between the poles of an electromagnet where the field is 0.8 Tesla. Find the cyclotron frequency. It has, few requirements: A, B, C, D, E. So let's start with A, and then we will continue. Okay, so cyclotron we discussed in class. This is simply a device, an instrument that gives us a very high speed particles, in this case protons. These particles used in other experiments, for example, to study nuclei of some materials. Element. Okay, so the principle of operation of a cyclotron basically depends on having a charge, in this case proton, inside electric field. The electric field operation or reason simply to give a speed, to give kinetic energy to these particles, proton in this case. So here we have a potential difference of 600 volt because we need to accelerate those protons every time they cross the gap or they reach the gap. Okay, so we have a charge Q. It's inside an electric field and also inside a magnetic field. Okay, let's calculate the magnetic field effect. Of course, whenever you have a charge, this charge has a velocity v. Inside a magnetic field, a force will be applied on the charge. The force simply equal to Q V B. In this case, it's F Q V cross B, but I'm trying to find the magnitude of the magnetic force. Simply it's Q V B sine pi over 2. Okay. This force is actually a centripetal force because it caused the path of the charge to change into a circular path. So this is simply equal to m multiplied by centripetal acceleration, which is v squared divided by r. Okay. So v with v will cancel out, and v is equal to q br divided by m. But also we know that v is equal to omega r. That means omega is equal to QB divided by M. And omega in this case is actually a cyclotron frequency. So cyclotron frequency, basically you find omega. This Q is equal to 1.6 10 to the power minus 19. This is for proton. Multiplied by B is 0.8, divided by mass of proton is 1.67 10 to the power minus 12. The question should provide this. You don't have to memorize it because I have done this many times, so I know. And you need to calculate this value. Let me use my calculator. Please always double check my numerical results. So this equal to, according to my calculation, is equal to 7.6 10 to the power 7 radian per second. Okay, so this is A. B, the speed at which protons exit the cyclotron. This should be easy because we have the equation for the speed. So B, V basically is equal to omega r. So we have these two values, and if you apply the r, in this case 0.35, the final answer will be 2.7 10 to the power 7 This is meter per second. Okay. C, their maximum kinetic energy. So their maximum kinetic energy, Ke max, is equal to half mass of proton multiplied by V square. Okay. I'm not going to put the numbers. I'll just try to use the calculator directly to see what will be the answer. Again, mass of the proton is 1.67 10 to the power minus 12 V square V. So this is equal to 3.7 to the power 6. Now, I'll just divide by the charge of protons. So let's get it in electron volt. What I did, I just divide this by 1.6 10 to the power minus 19 because I need the answer to be in electron volt. You could keep it as joule if you don't use this, because you know 1 joule is equal to 1.6 10 to the power minus 19 electron volt. So I just change it to electron volt, but you don't have to get the answer in electron. You could just keep it as joule. Okay. Okay, so D, how many revolutions does a proton make in the cyclotron? How many revolutions does a proton make in the cyclotron? Okay, so here the case. You need to understand the operation of cyclotron in order to answer this question correctly. Remember, when the charge moves between the D's from one side to the other side, what the electric field or the potential difference do to the charge? Well, it does the following things. Every time the charge complete one half revolution, every time the charge complete half revolution, the charge gets faster, right? Get faster, get more kinetic energy by the amount. So the kinetic energy change. So the delta K at every half turn will change by, you know, from the equation delta K plus delta U is equal to 0, right? So delta U is Q delta V. Means delta K every half turn is basically delta K changed by Q multiplied by delta V. Which means during one cycle, in one cycle, or one turn, let's call it, one revolution, one cycle, delta K changed by 2Q delta V. So every time the particle, the proton, moves around the complete turn, its kinetic energy changed twice, 2Q delta V. Okay, so the number of revolution, basically we could answer number of revolution, let's call rev, is equal to maximum kinetic energy, so kinetic energy max, which we got in electron volt, and remember this also would be in electron volt, divided by 2Q delta V, because in each turn the kinetic energy changed by this amount, right? Okay, so we have 2Q delta V, right? And we have this, so try to find that. For what time interval does proton accelerate? For what time interval? As delta theta divided by delta t, right? Remember similar equation for. So that means delta t is equal to delta theta divided by omega. Okay. Find delta theta basically because we have the number of revolutions, right? So that's why we need this answer, right? We have the number of revolution, but you know, in each turn, the theta changed by 2 pi, so you need to multiply by 2 pi, because delta theta is in radian, multiply by 2 pi, and omega is an answer, we got it somewhere, I think part A, right? So this is omega. Okay, so you will find in time second. Okay, so that's great. Okay, this is another question. We have a rod of mass 0.72 kilogram and radius r 6 centimeter rests on two parallel rails that are d equal to 12 centimeter apart and l is equal to 45 centimeter long. The rod carries a current of I is equal to 48 ampere in the direction shown in the and rolls along the rails without slipping. So the cylinder or the rod actually moving forward, right? A uniform magnetic field of magnitude 0.2 Tesla is directed perpendicular to the rod and the rails. If it starts from rest, what is the speed of the rod as it leaves the rails? Okay, so it looks like this rod is moving due to a force. In this case, it's actually magnetic force. It reached this point here. So the question asks for finding the velocity at this location. Let's call it V final. Here V initial is equal to 0. Okay, so this case actually is related to the case of a rod carrying a current, so and inside magnetic field, so F is equal to I L cross B. Here L is just denoted as D, okay? So this is our, instead of L is D, so we're gonna just write our equation as I D cross B. Okay, and the angle between D and magnetic field is 90 degrees, so basically the magnetic force is simply equal to magnetic force equal to I dB sine 90 is equal to 1. Okay, this force is going to be in that direction according to right hand rule. According to the right hand rule, if you apply it, your fingers would be on the direction of I or D, and magnetic field is downwards, so the force will be to the left. So this is the force, magnetic force. Okay. Now remember, this is a rigid object. It's a cylinder. It's rotating around an axis that passing through its center of mass. So we're going to use a conservation of energy. Work done by non-conservative force, we have done this in physics 1, is equal to delta K plus delta U. Okay. So the work done by non-conservative force is simply work done by the magnetic force, by this force, which equals to force multiplied by the distance, which is L, multiplied by the angle between L, displacement, and F, in this case cosine 0. So basically it's equal to FL, and F is IdB, so it's IdB multiplied by L. Okay. Delta K is equal to kinetic energy, rotational kinetic energy plus kinetic energy translation. We have done this in physics 1. Rotational kinetic energy is equal to half I omega final square minus half I omega initial square. Omega initial is equal to 0, I'm not going to write it, plus translational kinetic energy is equal to half mv final square, equal to half I is moment of inertia of the solid cylinder, which is half m r square. R is the radius of the cylinder, multiplied by omega final. Omega final, this is final, is equal to V final divided by R, so square, okay, plus half mv final square. Okay, so this is our delta K. Delta U is equal to 0. There is no change in potential energy. So that means I dBl is simply equal to these two terms together. So this is 1 over 4 m. R with R will cancel out. I'm going to take a V final as a common, plus half m V final square. You could easily find V final in this equation. Everything else known here. So get V final, none. Mostly the questions are, not very straightforward, because I assume you know how to solve the easy ones. So this question should give you good practice. In this figure, in figure means 28, the cube is 40 centimeter on each edge. Okay, it talks about this cube. 4 straight segments of wire AB, BC. So where are those? A, B, C, D. Okay, so these are A, B, C, D, DA form a closed loop that carries a current I is equal to 5 ampere in the direction shown. So current goes from A to B, looks like clockwise. Okay, a uniform magnetic field of magnitude B is in the positive y direction. Okay, positive y direction. Determine the magnetic force on AB, BC, CD, and DA. Okay, I think this is just a practice on this equation. F is equal to I L cross B. And of course using right hand rule. So in this case we have two vectors, we have L, we have B. L means the direction of L is basically the direction of the current. So if you use right hand rule, you basically place your fingers on the current and then you try to move toward B, toward magnetic field. The thumb should give you the direction of the current. Easy peasy. Okay, so for example, everybody should know there is no force on AB. So let's do part A. So for part A, if you apply this equation, it's going to be something like this. It's going to be F, I, L means AB. Okay, I'm going to just write down AB. This is AB. B is B. The angle between current and magnetic field is sine pi over 2. Sorry, just pi. Sine pi. Because the angle between current and magnetic field is pi, this is simply equal to 0. So no force will be applied on this piece. Right? No force will be applied on this force. Because current is just opposite to the magnetic field, so no effect. And then if you do for part B, if you apply, repeat this for B, you will do that. You will say is equal to I multiplied by length BC multiplied by B. Now the angle. Well, BC is located here, right? This is BC. And B is there, so the angle equal to 90. Right? So you will get the maximum value of the force. Sine pi over 2. So basically is equal to I. BC is 40 centimeter, right? So this 40 centimeter, let's just call it L. So this is equal to L multiplied by B. Okay. Now the direction. The direction is important. So how you find the direction? Well, you find the direction using right hand rule. Using right hand rule. So which direction should be the force? Think about it. Okay. So current going from B to C. So this is current. So current is on Z, right? On the Z axis. Current means towards Z. And magnetic field toward Y. So force has to be toward X or minus X. So which one is that? It's actually toward minus X. Minus X. Okay, so I could write this equation like this. I could say if for part B, remember I put a vector on it, so is equal to I LB, and I'm saying it's minus I, so people know it's opposite to x-axis, or simply just say opposite to x-axis. Easy peasy. Okay, The other part, this one. So I think this is part C, right? CD, part C. So C, let's repeat this. So F is equal to I, the length of CD, multiplied by B, the angle. Also, the angle is not 90, right? Basically, the angle is 45 here, right? Because magnetic field is, looks like magnetic field is here, right? So this is 45, because if you think about the perpendicular to this line, so this is 45. We got to be careful. So it's equal to sine 45. 45 in radian, of course. Okay, now what is CD? Well, this equal to I CD. So you have L basically is L squared plus L squared, right? L squared plus L squared and the square root multiplied by B multiplied by sine 45. Now direction, which direction is that? Well, direction of the force, I mean. Current goes this way. Magnetic field is going, so current is actually in the plane which is occupied by X and Y, right? X and Y. So it should be, the force should be on Z or minus Z. In this case, it's in minus Z. Minus Z. Minus Z means minus K. So you could write this equation, you could put arrow here, and here say minus K. Okay. Do the same thing for DA. The angle in the last one is easy. The angle is 90 degrees. The direction in this case is actually no. The direction is a little bit. The direction is actually going out of the page between X and Z. Between the X and Z. Okay. Now part E. Explain how you could find the force exerted on the fourth of these segments from the forces on the other three without further calculation involving the magnetic field. So the question simply tells us, is it possible to find the force on this if you know the force on the other three pieces? Actually, the answer is yes. If you remember the last example we did in this chapter, remember the example where you had a wire, straight part, and then bending part inside magnetic field that goes perpendicular or let's say y-axis. The final answer was the sum of the forces was equal to 0. And that's actually a general statement. Every time we have a complete circle, a loop, carry a current inside constant magnetic field, total magnetic field, a total force on it is equal to 0. Which means we don't have to do calculation for the fourth piece. What we do, we say sum of the forces is equal to 0. So you have four forces basically, right? So you say this. You say F of part A plus F of part B means their magnitude, okay? Magnitude. Plus force of part C plus force of part D is equal to 0. Okay. We know all those. So it's easy to find the last one. Okay, so basically the answer of okay, this question is in chapter 27, circuits. So we have a battery with EMF equal to 6 volt and no internal resistance. Supplies current to the circuit as shown in the figure. When the double through switch is open as shown in the figure, the current in the battery is equal to 1 milliampere. Okay. Means if the switch is as shown in the figure, the current is equal to this value. Okay. When the switch is closed in position A, the current of course change to a new value 1.2 milliampere. When the switch is closed into position B, the current in the battery is equal to 2 milliampere. And the question asks for find the resistance R1, R2, R3. Okay. So basically, if you look at the question, you have three different currents, right? One current when the switch is shown as is in the figure, and the second current when the switch is thrown to position A, and the third one when the switch is connected to point B. So we need three equations to solve for three variables, right, or three unknowns. Okay, so current in the circuit, current means the 1 milliampere, this current in the circuit is equal to the total EMF in the circuit divided by the sum of the resistance. Well, as shown in the figure, and if the switch was just simply not connected to neither to A or B, you will see that R2 is out of the question. So R2 is not connected. R1, R2, R3, basically just series. R1 plus R2 plus R3 equal to nothing, equal just to equation 1, let's call it. Okay. Okay, what about this current? Let's call it IA. This basically equal to the EMF of the circuit divided by the total resistance of the circuit. Well, if you connect this together, you will see these two, this one, R2 and R2, actually in parallel. These two are parallel, okay? And then their combination will be in series with R1 and R2. So basically you have something like this. It's R1 plus R3 plus the R2 and R2, both R2s are in parallel. So maybe you should do it just here. So R2 times R2 divided by R1, so R2 plus R2, basically equal to half R2. The parallel. So I'm going to say half R2. Equation 2. Okay. Now the third one, when you connect the switch to point B, equal to, so let's erase this, all this. When you connect these two, this is connected. Now R3 is out of the question. Why? Because this is short circuit. And R2 is out of the question. So current basically moves this way. Here it has two ways to go, R3 and short circuit, so it's going to go through this. This is discussing class, right? So R3 out of the question, R2 out of the question. So IB basically is equal to E divided by R1 plus R2. Question 3. I'm not going to do the complete solution, but this is easy. You could basically take R12 from here, right? So maybe I might just do one of them. I mean, get the value of one of them. So from this equation, R1 plus R2 is equal to IB divided by EMF. IB is 2 milliampere, so it's 2 10 to the power minus 3, and EMF is 6, so this is equal to 1 over 3 10 to the power minus 3 ohm, right? Now I'm going to take R1 and place it over here, right? So I'm going to use equation 1. I'm going to use equation 1. In this case, current is equal to EMF divided by 1 divided by 3 10 to the power minus 3, plus R3. Okay, so here you could find R3 because current is equal to 1 milliampere, 1 10 to the power minus 3, is equal to 6. So from here you could find R3. Then continue to find R1 and R2. Okay, so basically what we learn from here is when the switch is connected to point B, the current will not go through R3, because if you remember something like this. So let's say you have a direct connection and you have a resistor. Okay, current basically goes like this. It will not go through this resistor because this is short circuit. This is short circuit. So that's what we have here when this is short circuit. Okay, so this is similar to that. Also, whenever you have a case like this, for example, let's say you have a battery, you have a resistor, let's say you have another resistor, and you have something just hanging there. Okay. So current goes this way, goes that way. There is no current that goes through this. So that was the case of, when this is just hanging over there. So that should be the answer. Okay, this is an interesting question. We have this circuit. The circuit in the figure has been connected for a long time, so we need to understand what does that mean. If the circuit is connected for a long time, according to the lecture that I gave you on, charging, discharging capacitor, do you remember the charge on the capacitor? That when you charge a capacitor, the charge on the capacitor goes this way, right? So this is Q, this is T. It means the current in the capacitor and the branch that the capacitor is connected to it, the current will simply die out, goes to zero. Which means if the capacitor was connected for a long time, there is no current that passed through the capacitor because it's already charged. One side is positive, one side is negative. Now we don't know which one is which. So let's say, before reading the question, let's say this is A, this is B, this is C, and this is D. So what I'm trying to tell you is there is no current that passed through CD because it's connected for a long time. Okay, R1 is equal to 7.4. I'm going to just write down the value here, 7.4, because I'm going to need it. And R2 is equal to 6 ohm, so this is 6 ohm. Okay. The question asks for what's the potential difference across the capacitor. So basically we need to find VCD or VDC, doesn't matter. Okay. Okay, so here let's see. There we have a battery. So current, simply the main current start this way. Now at point A there would be a branch, right? So one current goes to the left, one current goes to the right. Let's call the current to the right is I2. Let's call this current I1. So notice this. I1 goes through 1 ohm and 6 ohm in the left. Okay. R1 goes through 7.4 and 2 ohm. No current will pass through the capacitor because of this node. Okay. So what I'm going to do is I'm going to apply Kirchhoff's rule. Before that, actually, Kirchhoff's rules one. So at point A, we know that I is equal to I1 plus I2. It's called equation 2. Now let's apply the second rule, loop rule, for the left loop. Left loop means I am trying to go around this from here. I try to go this way. Okay, I'll go clockwise. Okay, so my equation will be delta V equal to 0, and I'll go clockwise. So the answer will be plus 10. Okay. I1 goes through 1 ohm and 6 ohms, so basically it's minus 7 times I1 equal to 0. Easy peasy. So I1 is equal to 10 divided by 7, which equals to, calculation, I might do some approximation, significant digits, 1.43. 1.43 ampere. Okay, now let's apply the same rule to the right one. This time I'm going this way. Maybe I should erase this. This time I'm going from here to here, there, coming back, going here. Again, I'm going to do it clockwise. So clockwise means 10. Remember I2 passing through R1, which is 7.4 and 2 ohms, so it's 9.4. So it's minus 9.4 I2 equal to 0. This basically gives us I2, which equals to 10 divided by 9.4 It's 1 point, I'll keep it 2 significant figures, okay? Ampere. Well, according to this, now we know that I is equal to adding these two numbers together, so it's almost, let's say 2.5 ampere. Sorry, not I1, just I. Okay, good. Now we need to find VCD, right? VCD. There are different ways, okay? So basically you start from point C or D, doesn't matter. You start from point C and reach point D and calculate the total, calculate the potential difference across any component that comes between this point C and D. So there are many ways to go from between point C and D. You could, for example, you could go you could go this path. This is one. You could go this path. You could go from here all the way back here, but let's not complicate things. Okay, let me erase all those. I'm gonna go, let's say I'm gonna go from point C to point D. Okay, you could, of course, you should solve this problem, do the other paths, and make sure that you should get the same answer as I'm gonna get it now. So I'll start from point C and I'm applying the sum of the potential difference. Of course, in this case, will not be equal to 0 because I'm starting from point C. I'm not going back to point C. So it's going to be equal to VC. Now from C to A, I'm going against the current. So it's positive I1, which was 1.43. So 1.43 multiplied by 1 because the resistor 1. And now I'm at point A, I go toward point D, so I go with current I2, so it's minus 7.4 multiplied by I2, which was 1.06. Now I reach point D, so here is equal to VD. Okay, so simply move VC to the right side and solve for these two. I'm going to just solve it quickly. Using my calculator, so I got VDC, V minus C I mean, equal to minus, I get a minus sign, 6.4 volts. Minus means VC larger, okay? So that basically means VC minus VD is equal to plus 6.4 volts. So this problem simply tells me that VC actually is larger than VD. So what does that mean? VC is to the left, so that plate will be positive, this plate will be negative. That's the meaning of it. Okay, so that's one part. It was fun. Second part, even more interesting than the first one. Second one, maybe I need to erase some of those things here, maybe even here. Okay. The second part, it says, if the battery is connected completely from the circuit, over what time interval does the capacitor discharge to 1/10 of its initial voltage? Think about it. If this guy is just gone, you have the fully charged capacitor and you have 4 resistors. So think about these 4 resistors. I'm going to just redraw them this way, just to make things easy for you when you solve. So this is the capacitor. Okay, the two lower one, so these two these two resistors now will be in series because it will be like this. Okay. The upper ones will be in series as well to each other. So now this will be 7.4, 1 ohm, 2 ohm, 6 ohm. You could even change this one more time. This 2 is just basically 8.4. These two 8. These are also parallel to each other, not series, parallel. So I could make a single cap. So now this and this one are parallel. Okay, so you will have a single capacitor with a single resistor, R equivalent. Okay, that's easy now. and we have this guy totally charged, it will discharge, right? So you all know that Q is equal to Q max E minus T divided by tau, but also you know that Q divided by C is equal to C, sorry. So V, because the question asks for V, right? The question asks for, yes, for V, that's why I need the equation for V. So V is equal to, why I'm doing this, just basically just divide this by C, and that's it. You get the equation for V equal to V max exponential minus T divided by tau. So this is my basic, my starting point, I should say. But now I need to take care of tau. So what's tau? Tau is equal to R equivalent, which is this, multiplied by C. So what's tau? Well, R equivalent simply was, these two guys were 8.4 and this is 8, so basically is equal to 8.4 times 8 divided by 8.4 plus 8. Okay? Now, how we proceed? Easy. The question says if the voltage goes to 110, so I'm going to say if that voltage is equal to 110 of V max, what will be, at what time the voltage will go to V10? So this is V max exponential minus T divided by tau. You do that, you have solved a question like this, right? So you take a ln 1/10, and then you take ln with the exponential, will take each other's out. So T divided by tau. I assume you found, actually this is tau multiply this, I forgot to multiply by C, right? This C. So I'm going to put C here. Okay. I forgot this. Okay, so ln 1 is equal to 0, minus ln 10, so minus with minus will cancel out, and time simply is equal to in microsecond or whatever, let's say in second. Okay, that was a nice problem. Okay, this is another question. It's kind of difficult, I guess. We have switch S shown in the figure below has been closed for a long time. So here is similar to the previous question. That means the capacitor 1 and capacitor 2 are fully charged and no current passing through them, through C1 and C2. But doesn't mean the current in the circuit is 0. An electric circuit carries a constant current, takes C1, C2, R1, R2, so we have these values, kilo ohm and microfarad. The power delivered to R2 is equal to 2.4 watt. Find the charge on C1. Okay, and then it has another part. So let's do the first one. Okay, as we mentioned, because the switch was closed or has been closed for a long time, mean there is no current in C1. So current basically passing through R1 and R2. That's the current. No current pass through C1 and C2 because they are completely full of charge. Okay, so from this information, from power on R2, we could easily find the current, that current. So current here, or let's say power, let's call P2, is equal to I squared multiplied by R2. That means current is equal to square root of P2 divided by R2. Okay, I'm not going to put numbers here. Right away, use my calculator to calculate this. So P2 2.4, R2 is 7 kilo. So the answer is equal to, always check my answers please, 18.5 10 to the power minus 3 ampere. So this is current. Okay. Now from this current we could find the EMF of the battery, EMF. So EMF is equal to the current multiplied by R1 plus R2, because in this case both of them, I mean they are in series, right? Again, I'm not going to use numbers, just plug the numbers in my calculator. R1 roughly I'm going to write down is 203.5 volts. Okay. Now the question should be easy. Find the charge on C1. Find the charge on C1 here. Okay. Well, this point is basically this point. And this point is basically that point. So we could say voltage on capacitor 1 is equal to EMF of the battery minus voltage on resistor 2. So it's equal to I R2. Right? Because potential here is equal to the total potential, which is E, minus the potential on R2. Okay, so this equal to 203.5 minus current is 18.5. This is going to give us 74 volt. 74 volt. Okay. Let's find Q. So Q1 is equal to C1 multiplied by V across C1 equal to. So C1 is what? It's 3 micro, and here we have 74. So is equal to 222 microcoulomb. Okay, this is done. Let's also find, although the question did not ask for a charge on C2, let's also find this charge on C2, because I think we needed the second part. Charge on C2. So it's kind of similar. We say the same thing. This point, the same potential, this is same potential here. So V across capacitor 2 is equal to total EMF minus the voltage across R1, which equals to I R1 equal to. So we have the values, we have current, we have the other one, it's roughly 129.5. Please double check those. 129 plus 5 volts. Okay. That means Q2 is equal to what? CV, right? So is equal to C2 multiplied by V across C2, which equals multiply 777 micro coulomb. Okay. So basically this is part A. That's just extra. You might need it in the second part. Because second part I look at it is talk about C2, right? So second part it says, now the switch is opened. After many milliseconds, by how much has the charge on C2 changed? Okay, so I need to explain this. Let me erase all this, hopefully. Okay, see here. If the switch is opened, if that switch was opened, I cannot change it. Okay, some technical issues happened. My previous solution completely gone, but I hope it's within the video. I'm not going to repeat it. Of course, there will be current through the circuit, but if you wait a long time, after many milliseconds, the current will not pass through the C1 and C2, right? So, and if this is open, there's only two ways for the current, this way and that way. And because both paths, in both vertical lines, we have capacitors, so there are simply no current. No current will pass through it, which means at this case, the EMF here will basically goes to this charge, this capacitor, and also to this capacitor, because this is just parallel, right? So the question is asking for C2. We simply say Q2 now, let's call prime, because we found Q2 initially, right, before the video had some issues. Q2 prime in this case is equal to C2, but multiplied by the EMF, which equals to C2 is what? It's 6 micro. And the EMF, what was the value we found? EMF, I think it was 203.5, yes, I remember. It's 2 multiplied by 203.5, which equals to 1218. So Q2 equal to 1218 microfarad. And I remember Q2, we found it was 777, easy number to memorize. That's initially, before, that's when the S was closed. S closed. This is when S is opened, and we wait a long time. So I think the question asks for the difference between these two. So we say delta Q is equal to Q2 prime minus Q2, which equals to 1218 minus 777 equal to something in microcoulomb. Okay, so that was a very nice question, by the way.